Cool, cool. Now I'm going to teach about these things.
Hooray!
Hooray. So, an action potential is really cool. So I'm going to draw our fun little neuron. I'll make sure that that's, yeah, okay. So, actually I'm going to draw a graph first. I can use this as a graph. 0. Here's our fun line representing threshold. Move this line. Okay. So this is a drawing of what an action potential looks like in terms of voltage across that membrane.
Okay.
So we have ECF, ICF, cell membrane.
Ah, sorry.
So this graph describes like the change in charges across the membrane.
Okay.
So
So that spike would be like a big change in that positive and negative ratio.
yes, good, good. Okay, so there are several channels that I care about that I'm going to draw in here. So the first one, this is called our potassium leach channel. So remember we have high concentration potassium inside, very little outside. So potassium leaves the inside of the cell, which is what sets up our positive and negative charges along the membrane, giving us the negative 70 millivolts.
Okay.
That charge across. We have another channel. I'm going to use green. This is this one is our voltage gated sodium channel.
Oh, I remember that one.
Voltage NA. And then we also have here, I'm going to use purple. Yeah, good enough. That one is a voltage gated potassium channel. And then those are the main players within action potentials.
There's also a water one, right?
That's
That one
with
doesn't.
osmosis, not action potentials.
That's right.
There's a whole bunch of other channels that are in the cell membrane, but for neurons and action potentials, the ones that are the most important are these three.
Okay.
And during, literally at all times, this is always open, the potassium leak channel. So potassium is always able to just flow out and in.
Okay, makes sense, reasonable.
Okay, so different phases, great. So I'll start with the difference between a created potential and an action potential. So an action potential is when this voltage gated sodium channel, when that opens. So if this opens, that allows sodium to rush in. And the only way that this opens is if the cell hits what's called threshold. And for here, we'll say this is at negative 55 millivolts. So
Okay.
neurons that are ahead of this one will send signals to this one, and those will be added up together, if you remember the temporal and spatial summation.
Remind me.
So temporal summation is one sending lots of signals really quickly, and then spatial summation is if one is closer to where the signal would be sent for the future one. So if they're closer, spatial summation, further away but sending a lot, that'd be your temporal summation.
Sure. Okay.
So the cell body of the neuron will kind of just add up all of those together, and then it will see if it decides to actually send something. So right here, this little bump would be like some neuron in front of it is trying to get it to send a signal, but it's not enough of a voltage change for it to actually reach threshold. So then it goes back down and then say it sends another signal. And so that is enough to say something happened, enough sodium is coming in and causing a voltage change where this will then open. So before, during this entire time, the only thing that is open is this potassium leak channel. So then, but once the cell hits threshold, this activation gate opens, and sodium, which has a really high concentration outside and itty bitty inside, will immediately rush in. And what this does to our voltage across the membrane, I'm going to drop down here for ease, it becomes very positive on the inside and negative on the outside. And so that causes this huge rush. And
So
then
it just makes it more imbalanced.
yes, because the Nernst potential, which describes how badly sodium wants to go inside the cell, and the driving force is really high for sodium. So sodium really wants to go in the cell, and once it goes into the cell, it ends up going extremely positive because it gets close to what its Nernst potential would be.
Okay.
So after that, once it starts here, all of these open, and then during that time, the voltage-gated potassium channels will slowly start opening to allow more sodium to start leaving.
Leaving, so that starts to go down then.
Yeah, so this starts to, slowly become maybe a little less positively charged on the inside.
Okay.
And at this point, so you'll notice this little dangly thing that I drew right there.
Yes.
That is what's called the inactivation gate. So this was called the activation gate, that's the inactivation gate. When the cell hits here, after a certain period of time, this little ball and chain thingy kind of just sticks itself right in there. So now this is closed and sodium can't get in.
It's like a plug.
Yeah, exactly. So once that plugs up the channel, which happens right at the top, the only things that are open are the leak channels and then the voltage-gated potassium channels.
Which causes the sodium to leave.
Not sodium, potassium.
Right, yeah.
Potassium will
Of course,
leave.
the sodium's leaving too, right?
No, sodium can't leave because this is closed.
Ew.
So
right, okay.
the only time that sodium is able to cross this membrane, obviously given some exceptions, but within like general realm, the sodium is only able to cross the membrane in between here once it hits threshold and here, which is right when the inactivation gate plugs up the channel. And then after that, the voltage-gated potassium channel, all of those are open, and so that starts bringing the cell back down. So we're reducing the number of positive charges inside because we're moving more positive outside. And then eventually you have a buildup of negatives on the inside, buildup of positives on the outside, and then actually goes so far as to go even further lower than our resting membrane potential.
Okay.
And then eventually, once it hits a certain point here, these will close up again. So we'll remove that. So those will close up again. And then because of this leak channel, it'll slowly rise back up. Because this leak channel, potassium can go in and out.
Okay.
So potassium will reach some point of equilibrium. It's called stable equilibrium, so it could change, but it's stable. So then it ends up reaching that stable equilibrium here, and then is back at that resting.
Okay.
So yeah,
Kind of looks like a heartbeat.
interestingly enough, the action potentials will, I'm pretty sure that's what they're measuring,
Oh, really?
is the voltage across your heart. Because you have spikes which causes it to contract, and then, you know, the troughs which are relaxing. But I'm not certain, don't quote me on that.
How long does this take? Like this whole thing?
I'm about to talk about that.
Oh, really? Okay.
So, with this, so your neuron, depending on what it, like the kind of neuron and whether or not it's myelinated, will determine how quickly it can send signals. So your myelinated neurons, so the ones that say go to, we actually just talked about these today in class, you have alpha motor neurons. So they come from your spinal cord and then they go to muscles, and they're extremely myelinated. They can send signals as fast as like 300 something miles per hour. So like insanely fast.
Hey.
And so that will then get us into things that I'm going to talk about called the relative refractory period and absolute refractory period.
Okay.
So when we're at like this point down here, I think it's like here when this opens back up. So once we hit here, that closes, and then here, this closes, and then this goes back to normal. So at this point, this I believe is back to normal.
Which means unplugged and closed.
Unplugged and closed. So at this point, you could potentially get another graded potential strong enough to reach threshold and then fire it again.
Oh, okay.
So relative refractory period is how long like the neuron would prefer, quote unquote, to fire again. So the cell would prefer to reach threshold before it wants to send another action potential.
But it can.
But it can, because the voltage gated sodium channel is available to be opened if you change this charge. So if you have a strong enough stimulus coming from like a neuron beforehand, or if you have a stimulus that is going on for a really long time, so you have a lot of that temporal summation or a really, really big stimulus where like a whole bunch of things are saying like, hey, something happened, that could potentially get this to fire again at this point,
Okay.
because that could force this open. Because you have a ton of sodium on the outside, it doesn't require a lot to change this to flip it.
Sure.
And then your absolute refractory period is the time in which the cell cannot send an action potential, no matter what. And that has to do with the voltage gated sodium channel.
That one it's plugged.
Yeah. So this so once we hit this point, this becomes plugged. So sodium can't go in at all. And this only becomes unplugged as a function of time. So after a certain period of time, it opens again, and then the channel is reset. So during the time that it's plugged, it can't send another action potential because these sodium can't rush in and change the voltage.
Okay.
Make sense?
Yeah.
Great.
So-
Any questions?
So this, well, no, yeah, actually that question was answered too. Never mind.
Okay. You're good if I erase this all?
I think so.
Cool. You understand the difference between graded and action potentials? Graded is something that is either doesn't reach stimulus or potentially could push it further down. Oh, I didn't talk about hyperpolarization or repolarization. So depolarization is when your membrane voltage starts going up. So it's
Just
called,
like gradually?
yeah. It's just called depolarization, when it goes from that -70 up to something but in front of threshold. And then that spike, so from up to the peak, that's called the rising phase. That's as sodium rushes in and your voltage rises. And then you have the falling phase, which is when that channel is plugged, you have the voltage gated potassium channels open, which is trying to bring it back down. And then you have what's called the hyperpolarization, which is when it goes below resting, as these are still working on getting closed, and then hits back to resting.
Right, okay, makes sense.
Okay, now we're going to talk about capacitance. This is
Alright.
where we talk about the myelin. So capacitance is defined as C Q over V. This is a really exciting thing. So C stands for capacitance, V is the voltage, and then Q is the number of charges. Okay. So if I have a super thin neuron versus a really, really thick neuron with really, really big diameter. This is the inside, that's the outside. Imagine it's a sphere, circle. Tube, there we go, that's the word. Imagine it's a tube.
Cylinder.
Oh, yeah, I guess that works too.
That's the volume you're looking for.
So, nope, outside is. Oh yeah, no, outside is positive. You're right.
I am right.
That's right. So normal neurons say it's something like that. And this is at our normal approximately -70 millivolts. So what happens between these charges, because they're so close, they have a pretty strong interaction between them. Make sense? I will use red to describe that interaction. So each of those charges, more of its like energy is used in interacting and trying to pull the negative closer to it. So that means it doesn't have as much energy to force like the other positives away from it. So what that means is this has a really high capacitance, or basically how many ions it can shove within a space and still give the same voltage.
Okay.
It will make more sense when I talk about this one.
Sure, yeah, alright.
Actually, I will just not even use that one, I'll just use a myelinated one, because myelinated is nicer.
I agree.
So something with approximately same diameter, but instead we're going to put in our fun little myelin. So that's a myelin, they look like that, but
Yeah, that's anatomically correct.
yeah, this is an anatomically correct myelin. So what happens with this one is we're going to stick some pluses, and then we're going to stick our minus. So the interactions between these ones aren't as strong because they're so far away from their opposite charge. Make sense? So they're not pulling each other in as much.
Yeah, I mean that, yeah, okay.
But what they do is, because they're not spending as much energy trying to pull that in, they have more energy to push the same charge away, to repulse the same charge.
So each of the positives are a little bit more separated.
Yep. And this still ends up giving the -70 millivolts.
Okay.
So this has what's called a high capacitance, this has a low capacitance. So I can shove more ions and more charges with the same voltage. So because this goes up, that goes up. Here, because they're not pushing as much energy pulling in, they're using more energy to push each other away, I can't shove as many charges within the same area, which means my amount of charge goes down while this stays the same, so my capacitance goes down. Make sense?
It does.
So I can shove, higher capacitance means I can shove more ions within that space and keep the same voltage.
Okay. Does that mean that the closer to the edge of the myelin you get, the like closer those positive?
Yes, good. So that's actually a really good question. Are you looking up questions?
No, it just made sense to me.
Okay, cool. I like that. So
Basically, I'm super smart, actually. So.
it's true. I believe it. So with myelinated neurons, so you've got the myelin sheath here, myelin wrapping around, and then these little like spaces with bare axon is called nodes of Ranvier, some French dude. And so these have your really, wow, I'm gonna use a different marker now. These have your really low capacitance. And then in here, you've got really high capacitance. So what happens, actually really interestingly, so when your voltage gated sodium channel opens, you get a bunch of sodium in here. So you have a bunch of positive charges, and we like to call this the Bwong.
Long.
So what the Bwong is basically their sphere of influence able to continue to conduct the action potential down the neuron. So as I have positive charges here, they can affect the negative charges inside. Actually, I'm going to use blue for that. And by affecting these, they can change the charge on the membrane and allow more of these sodium voltage gated channels to open, which will then just continue to push it further down and send that action potential until it reaches the end and then sends a signal onto something else, or maybe activates a muscle like I just did, or like bowels or eyes, or literally anything. Any kind of effector.
Right.
That makes sense?
It does so far.
And so this is why myelin is super important, because it allows you to increase the power of this conductance. Not conductance, conductance is different. Just increase the power of the Bwong and make it, we were talking in class, and this actually is really cool, is the strength of this is potentially strong enough within your normal myelinated axons to make it like 5, 6, 7 segments of these down an axon.
That is pretty cool.
So even if you have like early multiple sclerosis, where like maybe you're missing some of these things, so you have a really high capacitance, you'll still be able to make it down and send impulses. Potentially not as quickly, but you'll still be able to send them.
Okay.
But once you remove all these, if you've got a really long axon and you've got a ton of these negative charges built up in here, this isn't going to make it as far because they're taking away from the Bwong's like power. Hence, if it's really bad, it won't reach the end and the action potential will just die, hence the paralysis.
Right, okay.
Make sense?
Yeah,
Cool.
yeah. Huh. That is interesting.
Now MS makes a lot more sense.
Yeah.
That's how I was when I was in class. I'm like, wait, really? I was gonna say like that's cool. I'm like, it's not cool, but it's cool that it makes sense.
Yeah,
Okay, now we're gonna talk about time and length constants. I wanna talk about the length constant first. We describe length constant as lambda, which is a big funky symbol for like this. And that is equal to the square root of Ri over Rm. And then you're going to say, well, it looks all Greek to me. And I'm like, you're right.
Well, I know what lambda is.
What's lambda?
It's a Greek letter. No, it's just used a lot in computer science, so.
Oh, cool.
Yeah.
So we want the length constant to be really, really high. If you have a high length constant, the power of that belong is really good, so it can travel really far. If this is really low, belong like gets impeded super quickly, and then the action potential could kind of just die.
Say again, with what gets low?
The belong.
No, like.
Oh, if the length
just
constant.
that. Okay, yeah.
Yeah. So if lambda is really low, belong is bad, and then doesn't get as far.
Sure.
I'm already at 25 minutes. I need to hurry up. Okay, so Ri is what's called internal resistance. So this is dependent upon like the thickness of the axon. So if I have a really, really skinny axon and I'm trying to send the belong through here, because that influence is so close to these negative charges, the belong kind of just gets weaker.
Okay.
But if I have a really, really thick axon, and you know these are all piled up at the edges, and I've got my belong coming through, these don't impede it as much because I still have quite a bit of power away from it.
Yeah, okay.
So
It's like
internal.
almost as if you have myelin sheaths.
Oh, actually, funny enough, that's what membrane resistance is, not internal resistance,
Right.
right? Yeah.
Correct.
Yeah, so that's what membrane resistance is. So that is effectively what having a myelin on there does, is it increases this.
Yeah, because everything's further away. So there's
Everything's
less
by the way, so
of those.
belong is stronger.
Okay.
So that's what Rm is. Ri is resistance to ions moving. So if
Okay.
I have a piece of bare axon, and remember I've got, say like, potassium leak channels and like a whole bunch of other channels, stuff moving in and out will actually change the power of my belong. Because if I've got leak channels here, potassium leaving, I've got more negatives on the inside, that ends up decreasing the power of the belong.
Right.
So, the cool thing about myelin is if I've got this big, thick, fatty tissue here, do I have any space for proteins and channels and stuff?
Probably not.
No, not really. So this means because I don't have a lot of movement of ions, this is really high. And effectively also basically extending the width of my axon, this becomes really low, which makes this uber high, which is why you want myelinated axon so your length constant is super high.
Okay, yeah. That makes a lot of sense.
Great. Now we're going to talk about time constant. Time constant is a little more funky. I don't remember what the letter is, so I'm just going to say T. And then this is the, I think it's the capacitance. So capacitance of the membrane times the resistance of the membrane. So if I have, and I want a really low time constant. Low time constant means this goes through faster. So if I
Makes
have a
sense.
low capacitance, so less energy spent of those charges interacting with each other and more energy repulsing each other, that's really low. And then membrane resistance, so how close those charges are to messing with the belong. So if both of those are really low, then time constant is really low and it can just go through faster. Good?
Good.
Great. Okay. Now we're going to talk about the chemical synapse. Woo! This is exciting.
Hooray!
So here's my synapse. They don't actually look like this, but this is an anatomically
that-
anatomically correct synapse.
Right.
And then there's our
Wrench.
dendrite.
I mean, dendrite, yes.
Yep, this is a wrench. So out here, actually, I'm going to draw several things, and then I will explain what they all are.
Okay.
Got those, and then I will draw.
Oh, I know what those are. It's holly, isn't it? It's all Christmassy.
No. Nice try.
Oh.
I will draw. Just draw those for a brief moment. Okay. So, this is what's called the chemical synapse. This is where chemicals are used to send signals onto the next set of neurons. There's also ones that are called, I think it's ionic synapses, where the synapse is like basically this, and there's literally like basically just channels connecting the two that allow the ions to pass through. But we don't care about those because they're actually super uncommon.
Right.
So what happens here is, we've got the Wong coming through. And so what that does is that changes the voltage over here. So the inside becomes positive and then outside becomes negative. This right here
Okay.
is a voltage B calcium channel. So this is a voltage gated calcium channel. When the Wong hits it, voltage changes, calcium will rush in. And the driving force for calcium, so how badly it wants to go into the cell, is even higher than sodium. So it wants to get in there really, really, really badly. These are called snare proteins. And so they have little binding sites that calcium will bind to. So calcium will bind to it. Calcium. And what happens is when calcium binds to this, these twist and pushes the little bubble, which is called the vesicle, which is made up of the same phospholipid stuff as the cell membrane,
Okay.
causes it to basically mesh with the outer membrane and then ends up releasing all of its chemicals that it's holding into the synaptic cleft.
Oh, interesting.
And so these little dots are the neurotransmitters. So that's your acetylcholine, your epi and ni, so epinephrine and norepinephrine.
Right.
So it will release those. So then we have a whole bunch of these out here in between the two neurons. And then eventually these will make their way over and they will bind to receptors on the postsynaptic neuron. This is the presynaptic, this is the postsynaptic, because, in front of, after the synapse.
Okay.
So when these bind, they can be either ionotropic or metabotropic, which are really, really fun words. Ionotropic just means it opens some kind of ion gate and allows some ion to come in or potentially go out. So say this is a sodium channel. So if this opens, it will allow sodium to rush in and then do its Wong thing.
Okay.
This one, the metabotropic, are a little more interesting. So they're what's called G proteins. And so those will send some little protein within the cell, and that will connect to something else within the cell, which kind of just leads to like a cascade of something happening within there. So those are the two kinds. Your metabotropic, which little something, and then the ionotropic, which just lets an ion in and out.
Okay. Reasonable.
And that's it.
Oh,
Any questions?
alright. I don't really know how to ask this, but like, well, other than, you remember the first video?
Yes.
There was you drew the membrane
Mhm.
and the different gates. There was one where it had like a key before it opens, right?
Yes.
That one?
That's what these are.
That's
Yes.
that one.
So
And
these are.
each of those proteins that thingy releases are keys for those particular things?
Yes.
Okay.
Good.
Yeah, I'm making connections.
This is actually really
Putting
cool.
This together. Okay. Cool.
Okay, so that's it.
Nice.